Okay, so today we're going to be talking about Chapter 1, and this will take us about 3 weeks and up through the first midterm. So Chapter 1 covers everything involved in quantum theory, or I shouldn't say everything, but at least what we're going to cover in this class for the most part. So we have a lot of things to cover. We're going to start with just general properties of waves and electromagnetism, because you need to have that as a backdrop to be able to talk about all the rest of the things and how we actually sort of build up an atom, or how we think about atoms. Now, from that point, we can kind of go on and we can start talking about the Bohr model, which we've already been introduced to a little bit, where you have the protons and neutrons in the nucleus and the electrons going around the outside. But what we'll see is that this only really works for the hydrogen atom and other ions that have one electron. So we'll start there and we'll talk about many things there, such as transitions and things of that sort, at which point we can move on and talk about more complex systems. But within the hydrogen, we can also then go on and talk about de Broglie wavelengths and quantum numbers, and then from there we'll start talking about multi-electron systems, atoms with more than one electron. And this is where we can start really getting into the idea of quantum numbers and how electrons are actually distributed within an atom. Whether we'll see that they don't actually orbit the nucleus in some sort of circular pattern, and we'll see exactly what that looks like and how we came about that that solution. You may already kind of know about s orbitals and p orbitals from your other classes. We'll be able to finally see how those are actually derived and what those actually look like and why we know that's what they look like. We're going to cover a lot of different theories and principles, so I have them listed out here for you, and we'll talk about each of those as we hit them. So first, a little bit of a history lesson for you, since this is important in the development of how these atom models came to be. So before 1900 or so, we always thought of atoms and molecules as just these rebounding balls. You can kind of think of them as billiard balls in 3 dimensions, that they were just sort of bouncing around. And we knew that there was more to it, but we didn't exactly know how. So this is the basis of theories such as ideal gas law, which we'll cover at the very end of this class. And it still works really well to describe certain phenomena. We can still use it for the ideal gases because for the most part it works. But this wasn't the whole story, and evidence kind of showed them that it wasn't the whole story. So around 1900, Max Planck came along. And this is when he was able to say, well, molecules and atoms, they're only emitting certain energies, and we'll talk more about exactly what emitting energies mean and how that works in a little bit. But that was a really important discovery, because at that point they knew there must be something called quanta, an amount of energy that you could have. And this meant that there wasn't a continuous level of energy, that these electrons must have some rules associated with them. And this turned physics upside down. They knew at this point that there must be something massive that they weren't getting that was important to look at. So we'll be able to sort of trace this line of thinking through the development of the different molecular models. So we have the plum pudding model, which was one of the really early ones. They knew that there are some positive charges and some negative charges in the atom, and they just didn't know how they were distributed. So they were always trying to come up with what do these atoms look like? So in the plum pudding model, it's exactly what it sounds like. You have this sort of blob of positive charge, and then suspended in that blob of positive charge is all sorts of little negative electrons. So you can kind of think of it like little raisins suspended in plum pudding. But once Planck came along and said, well, energy is quantized, there must be something else happening, that was when they said, well, there must be something else going on. Rutherford kind of refined this quite a bit and said, okay, well, all of your positive charge is now in your nucleus. He went through and did an experiment that showed that all the positive charge was in a very small space that didn't take up very much of the electron, or very much of the atom. So they knew that there must be something that later on would be called a nucleus. At the time, it wasn't termed that. Now, then, once quantization came about, this concept of different energy levels that Planck discovered, Bohr was able to take Rutherford's model and say, okay, now let's refine it a bit more. We think there's these energy shells, and the electrons are in the energy shell. Now, this Bohr model is probably what you've at least seen in high school, and we're going to use this for a little while. It's great for one electron systems, but after that it really breaks down. So in high school you may have learned that you had 2 electrons circling the first shell and then 8 and then 8. And we'll see that there's some similarities to that in the later ones too. Okay, now before we can talk too much more about atoms, we need to have a backdrop of what waves and electromagnetic radiation is, because without knowing that, we can't really go on with talking about hydrogen atoms and other atoms. So first of all, what is electromagnetic radiation? Well, a lot of what we see in everyday life is covered in this. You can talk about any sort of light that we see, or even things like heat. Heat falls into the IR category. Microwaves, sunlight, any sort of light that you see from light bulbs, X-rays. These are just kind of a smattering of the different types, but pretty much anything within this you can count. Radio waves is another one, so there's lots and lots of types of electromagnetic radiation. And we'll talk about what makes each one of these completely different here in a minute, because obviously microwaves, X-rays, and sunlight, and fire, heat doesn't all fall into the same category in our lives. So, some things that you need to know about waves and need to be able to define and figure out from information I give you. So we'll be talking mostly about transverse waves, but there's actually two different types. So the transverse waves is things you can think of light waves and all our EM radiation, but maybe in real life you're better off tying it to thinking about things like guitar string, or if I took a jump rope and I went like that and kind of made a wave out of it. All of these would be transverse waves, where you get this crest, and you can see that we have something called an amplitude, which is how high it comes from the 0 point, and a wavelength, which is from one peak to the other, or really any point on the line to that exact same point later on. And we'll talk about a few other things that we can calculate from this in a minute. Just so that you recognize that there are two types of waves while we're talking about waves, and that they all have the same properties, we can define all the same definitions, it's just a little bit different in look. We also have a longitudinal wave. And we won't be talking about that much in this class, but in your physics classes, you'll talk about them as sound and pressure waves. So now a little bit more about transverse waves and exactly what you're going to need to be able to know in this class. So here we have just sort of a simpler picture of it. And once again, we see the amplitude and we see the wavelength. Now we have something else, and that's called nu, or frequency. So this is not a V, it's a nu, it's kind of a squiggly V. And make sure you notice that, because we'll be talking about both V and nu in this chapter, and because the computer fonts make them look very similar, you're gonna have to know what they are based on context. And that shows up in a lot of cases. So what nu is this kind of, it's not speed, you don't want to think of it as speed, but it gives a measurement of how much you can get from here to here, how many cycles you can get in 1 second. Sometimes that's a little bit hard to think about in terms of a wavelength, but it's almost easier to think about in terms of spinning. So if I take and I spin around in a circle, and I do that once per second, that's my frequency would be 1 hertz, or 1 cycle per second. Same idea here. If it gets from here to here in 1 second, that's 1 hertz, or 1 cycle per second. And so that's how you want to think about frequency. Now, we can relate frequency and wavelength together, because if you think about it, the shorter the wavelength, the more cycles you're going to have in one time period. And so because of that, we can relate the two together. Now, they're related by c, which is the velocity, right? And because we're talking about light, we're talking about the speed of light here. And so if we want to calculate nu, or we want to calculate lambda, or wavelength, we can go back and forth by using the speed of light and using this equation. Now, I kind of have mentioned this off, the units for nu, or frequency, is seconds inverse, so that's 1 over seconds, or we can call that hertz. And the two are completely interchangeable. So, you get asked a lot, well, do I have to know what hertz means? Yes, because I can tell you, well, here's the frequency in hertz. And if you don't know that that means cycles per second, you might have some problems. So make sure you know that. Now, lambda, or wavelength, which is your distance from one peak, or one point on the wave to another, that's a distance. That's how far is it from one point to another. So that's just in meters. You'll see it done in nanometers a lot, And that's because visible light tends to fall in that nanometer region. And so because of that, there's a lot of times where it's just simpler to say 550 nanometers than 5.5 times 10 to the negative 7th. And so you want to get really good in this chapter at converting to nanometers and converting between all your metric units. So if you don't remember how to do that, that's all in the fundamentals section. Now, one more backdrop that you need to have sort of in your mind about how electromagnetic waves work is that there's actually two components to this. And in real research, in real life, we can make use of both of those components. There's an electric component and a magnetic component. Now, you'll notice if you look at this, and you can kind of see the blue and you can see the red, that these are going to have the same wavelength and the same frequency. The only difference is what axes they're on. If the electric field component's on this axis, then the magnetic one will be on this one. So they're 90 degrees to each other. So we're not going to do too much with this. It's just you need to have this sort of in your background. Now, because they're an electromagnetic wave, they travel at the speed of light. And so here is the speed of light for you, and we'll be using that quite a bit. Now, let's go back and talk a little bit about why all of those different electromagnetic waves that I talked about are so different, right? We had X-rays and microwaves and light and heat. What makes all of those so different from each other? So here we have the electromagnetic spectrum, and I have it listed out from, or I suppose this figure has it listed out all the way. Now, this little section right here is blown up so that you can see it, because that's the visible wavelength. That's kind of special to us because we can see it. But what you'll see here is that you have your radio waves, your infrared, which is heat, and then your visible, and then your ultraviolet, X-rays, and gamma rays. Now, this shows you the difference right here. You can see over in this section, you have a really high or a really long wavelength. And over here, you have a really small wavelength. Or in other words, you have a really high frequency right here. There's lots of cycles in one little area and a really low frequency here. And we haven't talked about how that's related to energy, but now we can a little bit. And we can say, well, okay, as you increase wavelength, you make the wavelength bigger, you stretch it out, you're going to have a slower frequency and you're going to have a lower energy. So things down here are really low energy, really low frequency, and really long wavelengths. So what makes radio waves different from something like X-rays, which we can actually use to visualize our bones, is all in the frequency or wavelength. So we sort of went over this already, but let's look at it again. As wavelength increases, it's going to take you longer to get from one cycle to the next, which means what's going to happen to your frequency? It's going to decrease. Now, let's look at this and say, well, which has a greater frequency, red light or blue light? Now, frequency isn't really listed on here, but we know that frequency and wavelength are inversely related. As as wavelength gets bigger, frequency gets smaller, and vice versa. So if you look at this and you say, which one has a greater frequency, red light or blue light, it's going to be blue light. Now, which one has a greater energy? We haven't done a lot of talking about how to calculate energy, but we can see that here, this is going to have more energy because you have a much faster or a much higher frequency and a much lower wavelength. And so your blue light will have a higher energy. Now, does blue light have a greater speed? We've said that it has a higher frequency and that it has a higher energy. So now, does it follow that it has a higher speed? No, they all have the same speed, right? It's all going to be the speed of light. That doesn't change. So all of them are going to have the same speed, but the frequency and the energy and the wavelength are all going to change. Now, even though I don't ask you to memorize this by any stretch, it is good to have a general idea, especially in the visible range, which ones are higher energy. And it's good to know that things down here are lower energy than things up here. And there's an easy way to remember this, thanks to this little comic by Foxtrot. So you have the little kid who he's kind of the smart genius kid in the comic, and he walks into a store and he says, "Do you sell ultraviolet blue?" The shopkeeper says, "Well, excuse me? Well, what about regular violet blue?" "No." "Blue bowl?" "No." Green, yellow, orange, no, no, no. Okay, rats, I'll take a Red Bull. So then he says, I was hoping for something a little higher energy. And then his friend says, well, at least it was an infrared bull. So, you know, the joke being that we talk about Red Bull being full of energy. Well, red is the lowest of the colors we can actually see. We should really be looking for blue bull or ultraviolet blue, or ultraviolet bull. Now, it turns out shortly after the first time I showed this comic, one of my students told me that they actually do sell a blue bull. I got all excited. Turns out it's actually just blue raspberry flavored. So, unfortunately, theirs is not just a higher energy. Okay, let's do an example exercise. So, we have a wavelength of green light from a traffic signal, and we know that it's centered on 522 nanometers, and we need to know the frequency. So when we look at this, we know certain things. You have to excuse some of the patterns. My computer crashed on me last night, so it's been completely changed. Some of the animations got messed up. So we know this, and when you're first starting out and doing a lot of chemistry problems, it's a good idea to go through and write everything out that you know and put it in a little table so that you can fill into equations or maybe figure out what equation you need. So this is sort of a good technique when you're first starting out, to just write down, here's what I know that I think is going to be useful in this problem. So you'll see here I have the speed of light written down, and I have the wavelength that was given. And then at this point I can kind of say, well, I need frequency, so I'm probably going to need to be using this equation. So the first thing you want to do is, this is in nanometers, and this is in meters. So we have to put them in the same unit. Technically, it doesn't really matter what unit you put it in, but in most cases, it's best to convert to the SI unit, or the base unit in this case, so the meters. And so we do that. So we divide by 10 to the 9th. Some of you might say, well, can I multiply by 10 to the negative 9th? I thought that's how I did it. You can do that too. Either way is fine, whatever way you prefer. And so we get this. We get 5.22 times 10 to the negative 7th meters. At which point, now we have meters per second in meters, and we can fill into here. So we fill in our speed of light, we fill in our wavelength, and we solve. Now, we need to check for sig figs in units always, right? You won't get all your points on your exam if you don't do that. So we need to say, well, we have 3 significant figures. This is infinite. Don't forget that's infinite sig figs because it's a definition. And so we put in speed of light to have 3 to match. And so we're going to round to 3 significant figures. Now, notice I changed this from seconds inverse to hertz. Doesn't really matter if you do that or not. You can put both of them, or either one of them there. Either one is right. Just make sure that you know how that they're actually the same thing, so that if I give you something in hertz, you know that you can just fill in hertz into this equation and solve for lambda if need be. Okay, so now let's do some more examples, and we'll actually just work these over on the document camera for a change of pace. Okay, so here we have the frequency of radiation from your microwave. It's 120 gigahertz. So we need to make sure we know what giga means. So this goes back and tests all that stuff that I asked you to study in the fundamentals chapter. So we need to first convert that. We can't have 120 gigahertz. So we need to go ahead and change that times 10 to the 9th. So this is sort of the opposite. Now we have to multiply by 10 to the 9th. Now, something that's kind of useful to get used to doing here is I'm going to show you how I would actually write this conversion factor, because you're not going to give this to me as an answer. You're going to use it in something else. So rather than go through and type that into your calculator and risk making a mistake, it's completely okay to just write out 100 times 10 to the 9th hertz. And then use that for all your calculations. And it saves you a little bit of time, a little bit of button pushing, and a chance to make any mistakes when you're button pushing. So now we look at our equation and we say, well, how do we solve for wavelength? So that was the version of the equation that I gave you. You'll have to look at your equation sheets to see what I give you on the exam. But either way, we just need to solve for lambda. So however the equation is written, we're going to solve for that. So we can fill in our lambda equals c over nu, wavelength equals the speed of light over frequency, and then we can fill in all our values. And we can bring down hertz here Now, of course, you could never leave an actual answer in 120 times 10 to the ninth, but it's fine to fill it into an equation. And we get our answer. And we check all our sig figs, and I chose to use 2 here because we only have 2 here. And so it doesn't matter how many I filled in for speed of light. I needed to fill in at least 2, probably 3 would be better. I happened to fill in 4, but this sets up that we can only use 2. Okay. So now we have one more. And now you're kind of getting the, actually, no, that one's for next time. We'll save that one for just a moment. Okay. So this is a problem I have set up for you guys to do at home. So I have the answers for you there, which isn't included in your worksheet, so you may want to write that down. And you're going to do this one exactly like how we did that as extra practice. Okay, so now moving on a little bit, so you get a little bit more of a history lesson again. We have Planck's quantum theory. So this is going to go into a little bit more of what Planck actually discovered. So when he says that when solids are heated, they emit radiation. And we can see this to some extent in everyday life. Well, maybe not lava in everyday life, but you know that lava glows red. You know that if you turn on an electric heater, it's going to glow a little red too. And a light bulb, of course, and other lights. Now, they knew this before Planck. This wasn't something that was a secret or anything. Now, the difference was they never could really explain it. They could get close, but whenever they would try to mimic the pattern of how solids did this, it always really messed up at either the far on one side or the far on the other. They could figure out the middle, and they could explain the middle using all of the atomic models they already had. But either at the UV or the IR areas, far out in the directions, it would mess up. Now, once Planck came along and said, well, okay, these molecules are not actually emitting a steady stream of light. They're emitting energies at very specific, or they're emitting light at very specific energies, and that we're going to name these quantum. That changed things. So what a quantum is the smallest quantity of energy. And that's going to have an equation, and that's equal to E equals h nu, or E equals hc over lambda, whichever way you want to think about it, whichever way is useful. So you want to think of this quantum as a little energy packet, and it's the smallest energy packet. So lots of things in life are going to be quantized. You don't want to think of this as some sort of weird concept. It's not that bizarre when you think about it. So something you can think about in everyday life, our money system is quantized, right? You can't really get less than a penny. Now, sure, with modern accounting techniques, they do things like that. But if you're talking back just trading cash money, you're not going to have less than a penny. And so that's kind of a quanta, right? You can't have half a cent and hand half a cent to someone else. So just think of this as the smallest unit of energy. Now, h is called Planck's constant, and that's 6.626 times 10 to the negative 34th. No, you don't have to memorize, but yes, you'll probably have it memorized by the end of this chapter because you're going to use it so much. And so this is just a constant that you're going to fill into there that gets you to the answer that you need. Okay, so now we have another example exercise. So we talked about a green traffic light in our previous problem, and we said that the wavelength was 522 nanometers, or most of them were 522 nanometers. We had calculated the frequency doing that. Now I say find the energy. So once again, here's what we know. We know C, we know lambda, and I went ahead and converted this right here, so we have it. Now we also know this. Now you may say, well, can I use E equals h nu too, since I know nu? We figured that out in the last problem. Sure, you can. In general, you don't want to use things that you've already calculated once, and using that in another problem if you can avoid it. If you can't avoid it, and you obviously have to, that's fine, but you don't want to have to, if you can avoid it, you want to, because if you got nu wrong, now you're going to get this one wrong. So we're going to go back and we're going to use lambda, which was given in the problem. So we have our equation, and we can fill everything in. Planck's constant just gets filled in as is. So joules seconds, we fill in C because that's just a constant, so we know that. And then we can fill in lambda, making sure that we match the units here and here. Now, It's always good when you're filling in these equations to make sure all of your units work. So you can watch meters cancel here. You can watch seconds cancel here. And that leaves us with a unit of joules, which is an energy unit. So everything should work out fine. And we get 3.81 times 10 to the negative 19th joules. So that is that we have our right unit and we have our energy. So that's the energy of a green traffic light. Okay, let's continue on with the problem that we were doing before. Now we're going to find the energy of our microwave. So this time we're given hertz, which means that we'll start from E equals h nu. And we fill in h just as from the slides. Watching our units. Now we have to fill in the 120. Of course, we can't just fill it in 120. We need to convert this to hertz. And I'm going to do it right within the problem. So I'll just multiply times 10 to the 9th here and call it hertz. So sure, improper scientific notation once again saves some time and doesn't hurt the problem at all. Okay, so then we come down here. We type that into a calculator. We figure out how many sig figs we need. Now, notice I took hertz here and I canceled hertz in seconds. You know, that's one of those you want to keep in your head what hertz means. It really means inverse seconds. It really means 1 over seconds. So that's going to cancel there. Now let's round to the proper sig figs. So h doesn't matter. This has 2. And so we need to round to 8.0 times 10 to the negative 23rd joules. So now that we've done this, okay, we've seen that E is equal to h nu. We've seen that we have h and that we have 120 gigahertz. And we've noticed that hertz is equal to 1 over seconds. So that will cancel here. And we can go ahead and we can say, well, since E is equal to h nu, we can fill this in with this. Now, if we get this in our calculator, we need to make sure that we still go ahead and figure out our sig figs. So we have 2 sig figs here. So we bring these 2 sig figs down. We have 8.0 times 10 to the negative 23rd. So just like what we did on the slides, only with our other equation. So now on the slides, I sent you home a couple of similar exercises to do. And so go ahead and you can write down those answers if you need them. Okay, so moving on with this idea of black body radiation now. This is the idea that all of our solids emit some sort of light. And you might say, well, okay, that's fine, but when I look at, this countertop, it's not emitting any light. When I look at whatever, it's not emitting any light. And yet when you look at something like a heater or an electric stove or something of that sort, now you start seeing red light. So what's the difference between something that's just sitting and something that's glowing red hot? Well, kind of gave it away there, right? It's glowing red hot. So that's because it's warm. The temperature is increased. And that's why you start to be able to see the glowing. Now, if you look at something even warmer, like the sun, or some other stars out and about, you're going to get white light. Or you look at, from the light bulbs, you get white light. So what the problem is the reason we can't see all black body radiation is because it's not in the wavelength that we can see. Our eyes only see certain wavelengths, and we don't see wavelengths until it hits a certain temperature. So that means that the temperature affects what wavelength it's emitting. So here we have a graph that this is intensity, this is wavelength. And so as your wavelength increases, you have your wavelength over here, and what these lines show you is the profile of what wavelengths are being emitted. So if we have something at 3,000 Kelvin, arguably pretty warm, this will go ahead and it has this distribution. So you only see a little bit of light here, and most of it's sitting in the IR region. Now if you go up to 4,000, well, now you see a lot more light that's in the visible region. Your lambda max is still here, and then here, and then here. So each one of these temperatures shows you where the distribution of the photons are. So what this graph means by intensity is how many photons or what percentage of photons have that wavelength. So you can kind of think of it like your grade distributions that you're used to seeing. How many people have an A? How many people have a B? How many people have a C? Well, this is how many photons have this wavelength? How many photons have this wavelength? How many photons have this wavelength? So it's the same idea. And you can see as it gets hotter and hotter and hotter and hotter, it moves over more and more into the visible wavelength so we can see it. So that's why we're able to see things glow hot, the hot things glow, but we aren't able to see things at room temperature glow. Now, if you look at an incandescent light bulb, they glow, they have about a 2700 to 3300 temperature range. So given this graph, look at it for a second, why do you think incandescent bulbs are so inefficient? We don't use them anymore because of this. If you think about where would its profile be? Its profile would be like here, right? So when we look at an incandescent bulb, most of it we can't see. It's giving off plenty of light. It's just most of that light is in this region, which is that region. The region right below our visible spectrum would be the IR region, which we colloquially call heat. So most of the electricity that we put into an incandescent bulb is coming off in a region of the spectrum that we can't see. It's coming off as heat, and so that's kind of useless to us. We don't need to heat our houses with incandescent light bulbs. We want to light them with incandescent light bulbs. So something like a fluorescent bulb does a better job of lighting with less electricity because it falls into these higher ranges. Okay, so another example exercise. So so in this case, now we're looking at Proxima Centauri, our nearest star, and it's a red dwarf star. Now, it's about 4.2 light years away, which we don't really need too much for this piece of information. But we know that it has an average surface temperature of 3042 Kelvin. So we're going to work this problem a little bit backwards from what an actual astronomer would do, which an actual astronomer would take and say, well, we have this wavelength spectrum. They would have computers draw it out that could see all of the different wavelengths, and they would find the temperature of the star. In our case, we're going to just work it this way, which is a little bit backwards. So we have this equation from the previous slide. As far as why it's in millimeters, it's just kind of the standard way of doing it. So when we find this, we're going to end up with a millimeter value. So we'll solve this equation for lambda max. So in this case, I converted that constant that's in there to meters first. You could do it two different ways. You could just fill in and then get your wavelength in millimeters and convert that. Or you can convert this to meters. Either way is fine. And then for the sake of significant figures, there's also a 0 there. Kelvin we fill in as is. And we get this value. Now, if we look at what region of the electromagnetic spectrum it is, it might be a little bit easier to go ahead and convert this to nanometers, just for the sake of looking at this, which comes out to be 952 nanometers. So depending on how much you remember from the previous slides that we've done, this lines up right in the near IR region is what we call it. So it's near where we can see, but it's still in the IR region, which is right next to the red part of our visible spectrum, which is why when we look at a red dwarf, that's where it gets its name from, because the only light that we can see coming off it is red. And so we see it as red. Now, sure, there's this whole other profile that's in the IR region, but we can't see that. And so to our eye, we just see it as a red. And so that's where it gets its name from. Okay, moving on to some more history. So throughout all of modern-ish history, I guess you can't really call 300 BC modern, but even back then, there was some argument about what light really was, and whether light is a particle or whether light is a wave. So what does that fall into? Well, so this kind of went back and forth as each group figured out they figured out a little bit more experimental evidence that was a little bit better than the last person's and sort of proved the last person wrong. And once we started getting into, this region, now there started being really good experimental evidence either way. So it wasn't until Einstein came along and said, hey, you guys, stop arguing, it's both. So we're going to go through and we're going to walk through and say, well, why is light like a particle? Why is light like a particle? And why is light like a wave? And see some of this wave-particle duality that we call it. So first of all, why is it a particle? What treatment shows that it's like a particle? So we have something called the photoelectric effect. And the idea of the photoelectric effect is that you shine light onto a metal, and when you do that, you eject electrons. So the idea here is that and there's a lot of different rules for exactly what it can be, but you're ejecting electrons from a metal surface with light. So, and I should also mention, this is actually what Einstein won the Nobel Prize for. So in common culture, he might be best known for his theory of relativity, but this is what got him a Nobel Prizes. So it's is obviously very, very important. So now comes the part that we sort of show its particle. The energy of each photon has to be higher than what we're going to call the threshold energy, which means that each photon has to have a high enough energy, or think about, how is that related to frequency, a high frequency, in order to go ahead and eject an electron. If you don't have that per photon, it doesn't matter how many photons you shine on it. You can just, blast it with as much intense light as possible. But if it doesn't have that minimum frequency, it's not going to eject an electron. Now, we call that minimum energy the work function. So for example, violet light can eject an electron from potassium, but if you shine red light on it, so remember our little comic with Foxtrot, and we know that our blue and our violet are higher energy than our red. So violet light can eject an electron from potassium, but it doesn't matter how much red light, you're never going to get any. So if you shine a little bit of violet light on potassium metal, you'll get a little bit of electrons. If you shine a bright violet light on it, meaning more intense, you're going to get tons of electrons. Now, if you shine the brightest red light you could possibly find on that potassium metal, you're still not going to get any electrons. Okay, so what is the threshold frequency? How can we find it? Well, we can use E equals h nu to determine it, and then you just have to take off the work function. So we'll do some examples of that in a minute. So this is one of the major things that show the wave-particle duality of light. Now, if you want to do kind of a computer-simulated lab on how this works, I would suggest going to this webpage. They have a great simulation on it. It works best if you play with it on your own rather than me showing you how to play around with it. So I'm going to leave that for you guys. But go there and play around with it a lot. It will really, really help you understand on your homework and understand on all the conceptual questions I asked on the exam what's happening. So consider that a homework assignment just like everything else. Okay, so now looking at this in a little bit more detail. So this is the potassium example I had from before where I just sort of talked it through. Now, if you go through and you put in just enough energy to knock the electron loose. So in other words, it's going to be exactly the energy of the work function. So just a reminder, work function is the lowest energy you need to eject an electron. If you put on exactly that much, it's not going to have the ejected electron won't have any energy. You're putting just enough energy in to knock it loose, but not enough to give it any energy at all. Now, if the energy of the photon is higher than the threshold, so it's higher than just that work function, now there's extra energy there. Where is that extra energy going to go? Well, it has to go somewhere, and where it goes is into the kinetic energy of the ejected electron. So if you increase the energy of a photon, it increases the kinetic energy of the ejected electron. So here, if we look at this example, our red light, our lowest energy of the three lights, comes in, and that's not at the threshold frequency. And so that's not going to eject any electrons. Now, if you put in green light, that's high enough energy to go ahead and eject electrons. And it's going to do so at this speed. Now let's increase the energy again into violet light, so we get a much higher energy. Now, things to sort of note here, and when you play around with that simulation, you'll note this to some extent too. If you put in one photon, the most electrons you can get is 1 electron. So if you want more more ejected electrons, you have to put in more photons. Just increasing the energy isn't going to make more photons come off. It's just going to make them come off with a higher speed. If you're below the threshold frequency, no photons are coming off at any speed. You're just stuck there. You need to make sure you know the difference between intensity and energy. So the difference in intensity and energy is if I take these lights and I do that, or I do that, I've just decreased the intensity of light. I haven't changed the energy, but I have decreased the intensity. If I wanted to change the energy, this light doesn't actually work because it's white light, so there's a spectrum. But let's say I had little flashlights here and I shined a red light. If I want to increase the energy of those photons, I'd have to change it to blue light. So energy is very different from intensity. Intensity is talking about total energy. So if I wanted to make a red light more intense, well, I turn on 2 of those same red lights. If I want to make a blue light more intense, I turn on 2 of those blue lights. But that doesn't speak to the energy of the photons. That's all about, you can think of it as color. If it's in the visible region, it's what we see as color. If it's in the non-visible regions, the idea of color doesn't work so well. So if we want to figure out this kinetic energy, it's what's left over after you take out the work function. So we see h nu in here, or hc over lambda works too. That's our energy of a photon. So the incoming photon. And we just subtract out the work function. We say, okay, well, there's a certain amount of energy of that photon that's going to be taken away. It's going to be taken away and put into actually knocking that electron loose. So we subtract the W, and that gives us the kinetic energy. Now, what do we think happens if the intensity of light is increased, but the frequency stays the same? So remember, we talked about intensity. We said it's just more and more and more light. It's shining 3 bulbs instead of 1 bulb, or 10 bulbs instead of 5 bulbs. So if we increase the intensity, are we increasing or decreasing the number of photons? Well, we're increasing it, right? What our eye see as being more bright means that more photons are hitting our eye. And so increased intensity means more photons. And the more photons you put in, the more electrons you're going to eject. So in that case, you would get more, just to restate that one more time. As you increase the intensity, you increase the number of photons, thereby increasing the number of ejected electrons. Okay, so let's walk through and do an example on the board with this. So we have calcium's work function. So now I've actually given it a number. We call it a work function, but in your guys' case, it's always going to be a number that I'll either give you or I'll give you enough information for you to find it. And I ask, what is the minimum frequency of light for a photoelectric effect for calcium? Now, I could ask that a little bit differently. I could say, what is the threshold frequency? I could ask you the energy. I could ask you the threshold energy. So make sure you know that term threshold. That just means the minimum. I could also ask you the maximum wavelength of light. So keep that in mind. Minimum frequency corresponds to maximum wavelength. Okay. So then I say calculate the kinetic energy, and that's something that you're going to see a lot in this chapter. You're going to be doing 2 or 3 things with these equations, working back and forth. So we're going to find the minimum frequency, and then we're going to find the kinetic energy of the electron if we now put this in. So the work function will tell us the minimum frequency of light you need, and then we can find the kinetic energy of that. 2 different problems. So I wanted to put this in here like this because you will see this in your book, and you'll see this on the internet and other random sources. So this is just another way of writing the work function. So don't think anything of that. I wrote it both ways so you can get used to seeing it both ways. Now, if we look back on our last slide, we know that we're going to need this equation. But we don't have something. We're missing something. So if we have our work function and we need to find frequency, we need to have kinetic energy. But we don't have kinetic energy, right? Well, we do. What is the kinetic energy at the threshold frequency? At the threshold frequency, remember, you're putting just enough light to knock the electron loose, but not enough light to actually give it any speed at all. So you're knocking it loose, but there's no speed or no velocity. So your kinetic energy, think back to your fundamentals, is 1/2 mv squared. So if there's no velocity, there's no kinetic energy. And so your kinetic energy is equal to 0. And so because of that, h nu minus the work function is equal to 0. Well, now we know h, and we know work, and we can just solve for nu. And so we end up with this. So this is sort of the trick to making sure that you can find your threshold frequency. You have to remember that at your threshold frequency, your kinetic energy is 0. And that's because your velocity or your speed is 0. There's not enough energy in that photon to actually give the electron any speed. And so it's just going to knock it loose, and it's not going to move anywhere. And that gives you your threshold frequency. Now, we can go ahead and also figure out our kinetic energy if we have this frequency of light. So these are sort of the two of the main ways I can ask this question. Now we have this, and we need to go ahead and find the kinetic energy. So we fill everything in. We fill in our h, we fill in the frequency that was given, and we fill in our work function that was given. And we get this. Okay, so one more. Now, notice in this question, we're taking it a little bit further. We're saying we have the work function for magnesium. We're calculating the minimum frequency of light required to eject the electrons, so that's the same thing we just did. Then we're calculating the kinetic energy if we change the frequency of light. So again, what we just did. Now we're going to take it one step further, though, and we're going to say, well, what about if we also want to know the velocity? So that's sort of the extra step that we're going to do here. Okay, so we're going to start the exact same way that we started in the last problem. So we start from our kinetic energy equation. And we remember that, well, at the threshold frequency, our kinetic energy is equal to 0. So we can set that equal to 0, which now means that our nu, our frequency, is going to be equal to W over Planck's constant. So we can just fill those numbers in. So we have this. And Planck's constant. And we can get our number. And of course, you can write it in hertz, or you can write it in 1/seconds, or you can write it in second inverse, whichever way you want to do it. And you'll see your joules cancel, so that makes sense. So that's our threshold frequency. That answers the first part. Or in other words, to eject the electrons, our minimum frequency, our minimum energy, our longest wavelength. Now, we can go through and we can do the second part. What if now we're given a frequency of light of that? What is our kinetic energy and also our velocity or our frequency? Okay, so we go back to this equation again. Maybe I'll draw a little line here so we know that we're starting a separate section. And once again, we're just filling everything in. So we fill in Planck's constant. and we fill in our frequency. And we subtract out our work function. Now, that gives us our kinetic energy. So we fill that into a calculator and we solve. And we get our kinetic energy. But I also then asked you for one more thing. I said, what's the velocity? So now we can't quite end here. So this is kinetic energy. Now we need to find the velocity. So in order to find the velocity, we have to remember what our equation for kinetic energy is that we've used before. So right now we've been using this equation because that's what works for this particular system. But there's also the very general form of kinetic energy. And that is 1/2 mv squared. And so we can go through and we can say, well, okay, now what is our velocity? Keeping in mind that it's an electron. So if we know our kinetic energy, and we know that that's equal to 1/2. Now what is m here? Well, m is our mass of an electron, so that's something that we would look up. On an exam, I would give it to you. And then we would have v squared. Now notice this is one of those places that we get into the idea of we have both frequency and nu, and they're in one equation. So make sure not to mess them up. This was nu for the threshold frequency, this was nu for this frequency, and this is v for velocity. So now we go through and we solve this. And we get our velocity. So that's sort of the other way that you'll be asked to do this on a relatively regular basis. And of course, the backwards directions of all of those is fair game as well. I can always give you the frequency and ask you for the kinetic energy, and then ask you to use that kinetic energy to solve for the frequency of light that was actually given. Now, this comes up in your book, and so I wanted to have you guys look at it a little bit, and it comes up in your homework, and I think it's good to always look at these graphically and see what's happening too. So in this graph, we have 3 different metals. And you can notice something about this. It's linear, right? As you increase the frequency, you increase the kinetic energy. And you do that linearly. Now, it's linear up until a certain point, or I should say after a certain point. Before that, it's just 0. So when you look at this in your book and you're asked questions on it, you can see that this is just 0 until you hit this threshold frequency. And at that point, it's a linear relationship. Now, what is that linear relationship? Well, we can look at the equation to show us that. If we have this equation, we can kind of look at it as y equals mx plus b, right? So if we look at this as y equals mx plus b, where this is our x, what is our m? Well, our m would be h. So our slope here is h. And so that's one of the places where you can sort of derive h out of. And you can say, okay, well, h is a constant that is going to be given to me, but it does come from somewhere. And this is one of the places where you're going to be able to see it kind of show up. And you can actually graph it and you could find the answer. So you're asked to do that at some point where you have to fill in a graph and you're given the incident wavelengths and you're given, or frequencies, and you're given the kinetic energies, and you have to graph it, and then you solve for the slope, and then that's what gives you h. Okay. So that's kind of gets us through the particle aspect of this. So keep this in mind as you're doing your homework, that this is a good graph to have in your mind. It's going to increase as you increase the metals, and that sort of wraps up the photoelectric effect and the sort of particle aspects of this. Next time, we'll go into more of the wave interference and more of the ways that we can look at this and say, okay, well, light might act like a particle here, but it's definitely a wave too. And so there's experiments just like the photoelectric effect that will go ahead and show us that.